All right, we're going to start with 2.8 now, the intermediate value theorem. This theorem is an important theorem in calculus, and a lot of calculus is built upon this, as well as the mean value theorem. So we're going to get a little bit of exposure to this. So the intermediate value theorem, what it says is fairly simplistic, and that is essentially, we'll explain this through example 1 here. So in the plane R2, plot two different points, and let's just make sure that they're separated. They're not directly above one another. So I'll draw my basic axes here to create which creates our plane, and then I'll create two little dots. I'll put one here, and I'll put one here. Okay. In other words, not right above each other, so we didn't want it like this. Okay. So now it asks us to draw a horizontal line in the space between the two dots. So I'll just draw some horizontal line. Okay, let's go ahead and say this is y equals L, where this value L is something above this y value at this point and below this y value at that point. So now, using red, let's go ahead and let's also label these points A, comma B. Let's go ahead and try to connect these two dots. So we'll start at this dot down here and go to this dot up here. The question is there any way using a single stroke to connect these two dots without crossing the line? And no, we can't do something like this, right? Because this line does go on forever. So unfortunately, that does not work. Is there any way that we can connect the two without lifting up our pencil? No, there's no way to do it. No matter how hard we try, we have to, at least at some location, cross this line. So this is the x value right here where this crossing of y equals L occurs. So the intermediate value theorem basically says the following. If you have a function, okay, let's say this red curve is our function. So let's say that's our function f. So I'm going to read this theorem 1 here, the intermediate value theorem. So if f is continuous on some closed interval a to b. So if we look at the portion of the graph between a and b, clearly f is continuous there. Okay, so that's one stroke. And that this y value down here, f of a, and this y value up here, f of b, if they're not the same. In other words, there's some separation here. There's some distance. There is a gap. Then, for every value m, so let's go ahead and actually, I guess I'll make this blue line y equals m just to make it line up with our theorem. I thought it was L. My apologies. So, pick any value between the lower y value and the upper y value. Pick any y value. Then, if your function's continuous between them, then there has to be some location, some number that is bigger than a but less than b, where this graph crosses the blue line. In other words, if you know the value of your function is one number, let's say 2, and later on it's 4, then every single real number between 2 and 4, even pi, your function at some location between a and b achieves that value. And that's all the intermediate value theorem is. And it's really making a statement that if you have something that changes continuously, then if you know its value at two different locations, then you know that that function had to achieve or have every single value in between. Which is a really obvious fact, but it's a really important characterization of continuous change. And since calculus is the study of continuous functions and how they change, it's absolutely essential.